Hello everyone, I'm Mohammad and I'm going to present Bedrock, which is a platform for PBFT analysis, implementation, and experimentation. And we have started this work when I was a PhD student at Santa Barbara under Amr and Divi. And later on, I became a postdoc at UPenn working with Boon, and Sadoghi, who is here, was one of our close collaborators that time. So as we all know, distributed systems use consensus protocols, use fault-tolerant protocols to provide high availability and robustness. Let's talk about a simple example, a banking example. The bank replicates the data on multiple servers, and the client talks to bank, sends the transaction to one of the servers, the leader server. The leader assigns a sequence number to this request, broadcasts it to all nodes. And then if we have sufficient votes, then the leader can commit the transaction, and everyone is going to execute the transaction, execute that transaction. So we all know that we use state machine replication. Thanks to the previous speakers, we all know what is a state machine replication. And the goal of a consensus or a BFT protocol, a consensus protocol here is to assign order to each client request. And then transactions are going, or these requests are going to be executed in that order. So here we talk about example where we support crash failures. We are able to tolerate crash failures, where basically a faulty node stops working and it doesn't behave maliciously. But there is a more interesting type of basically failure or a failure model, which is Byzantine. And in a Byzantine failure, node can fail arbitrarily and potentially behave maliciously. So the kind of the gold standard for Byzantine fault-tolerant protocol is PBFT. PBFT runs in 3 phases of communication. 2 of them have like O(n) square complexity. And assuming that we want to tolerate at most F failures, PBFT requires 3 F nodes. But the problem here is, the challenge here is PBFT is not the only protocol that we are aware of. There are many BFT protocols, and there are like more than hundreds of these BFT protocols around. And if we want to choose one of them for our application or for the systems that we are designing, it would be challenging. So the goal of this Bedrock platform is to help us in answering this question, what protocol best fits our needs. And it does that in with different ways. From the analysis point of view, Bedrock helps us to understand these protocols, to compare these protocols, and interestingly, to move from one protocol to another protocol. From the implementation point of view, Bedrock provides a domain-specific language that protocol developers can write their protocol in a simple language, and the Bedrock provides the implementation for that protocol. And finally, since all these protocols are implemented within the same platform, we can have we can evaluate these protocols in a more fair and unified manner, in a consistent way. So let's start with analysis part. So in Bedrock, we provide a design space for protocols. Basically, we provide a design space with 20 dimensions. Consider it like 20D space, and then each protocol is a point in that design space. And then we provide some design choices. Each design choice can show a trade-off between 2 or 3 dimensions. So you can see each design choice as a one-to-one function, that you take the design choice and go from one protocol to another protocol. Basically, we show the trade-off between these 2 protocols. The focus of Bedrock at the moment is on partially synchronous PFT protocols. So I show a toy example. As I said, there are 20 different dimensions. But here, let's assume there are only 2 dimensions: the number of commitment phases and the number of replicas. The number of commitment phases could be, let's say, 1, 2, 3, and the number of replicas could be 3F plus 1, 5F plus 1, or 7F plus 1. We have points in this design, basically this space. The green points are the valid protocols, the protocols that exist, and the red points are the protocols that are invalid. For example, we cannot have a protocol that has 1 commitment phase and it requires only 3F plus 1 nodes. The design choices that I mentioned is basically switch from one protocol to another protocol. So you can have a protocol with 3 phases of commitment phases and 3f+1 nodes. And then this design choice maps this protocol with a protocol that has 2 commitment phases and 5f+1 nodes. You see the trade-off. We reduce 1 phase of communication by adding 2f more nodes to the protocol. So to talk about this design space and different design basically choices that we have, let's talk about different stages of replicas in a BFT protocols. We have clients, we have a set of replicas. Clients send requests to replicas. We have ordering, where we establish an order among transactions. We execute transactions. And after the execution, we have view change, where we basically replace a leader that is suspected to be faulty. Another stage is checkpointing, where all basically replicas communicate with each other to basically checkpoint the state of the data. And we have recovery protocols that are used to recover a faulty basically replica. So for example, for PBFT, we have seen this part, which is the ordering phase, but you can see the view change. When the leader becomes faulty, a new leader comes in, and it starts a new view. And we have recovery. We have proactive recovery, where we basically recover nodes periodically. So talking about the design space of BFT protocols, here is all the dimensions that we have considered. And this is not supposed to be an exhaustive list of things. We just want to show the method that Bedrock provides. And we can add more, basically, dimensions to this design space. The Bedrock platform provides this opportunity for us to add more dimensions. So we can talk about these basically dimensions. The commitment strategy is talking about like whether a protocol is optimistic, pessimistic, or robust. An optimistic protocol assumes some optimistic assumptions, like on the synchrony of network, on the failure of nodes, assume, for example, all nodes are non-faulty, or on the contention between transactions, we can assume that. The number of commitment phases, it could be like 2 commitment phases, 3 commitment phases, and the view change, whether it is a stable leader or rotating leader mechanisms. The checkpointing mechanism, the recovery mechanism, the type of clients. Clients are only proposer, or they can help in repairing the protocol. Talking about environmental setting, we can think about number of replicas, whether like 3f+1, 5f+1, 7f+1. The communication topology, whether it is like a star communication where we have linear communication complexity, or it is a clique where we have n² complexity, or it could be a chain topology, or it could be even a tree topology, so different basically topologies that we can consider. The authentication is based on max or signatures or threshold signatures. Whether a protocol is responsive, what are the different timers that we can use. And then talking about quality of services, whether a protocol provides order fairness or provide load balancing or not. And there are many performance optimizations. Once we have these design dimensions, we can talk about design choices. So each design choice, as I said, is basically talking about different design dimension and mapping from one protocol, one set of protocol to another set of protocols. For example, linearization, we can make a protocol linearizable. Or we can reduce one phase of communication by adding more basically nodes. There are different design choices, like providing a fair, making a protocol fair, making a protocol robust, and other. I'm going to talk about a few of them. So for example, linearization, what it does is basically, we have PBFT, and it basically replaces each phase of PBFT, each ON² communication phase of PBFT with 2 linear phases. And as you can see, there is a collector, possibly the leader, that collects all these messages and sends them. And if it receives sufficient number of messages, it sends it to everyone. And it requires to provide some certificate that it has already received these messages. So we can go from like this ON² protocol to this linear protocol. We can provide a fast protocol by reducing one phase of communication, but adding 2f more nodes to the protocol. So we remove this phase of communication, but the trade-off is we need to add 2f more nodes to the protocol. Another design choice is leader rotation that has been used in hot stuff. So basically, we use we have a kind of a view change. We add phase here in the communication, but then there is no need for view change mechanism if a leader fails, because we already rotate the leader after every round. Or this could be some optimistic or speculative execution, something like Ziziva, that gets rid of these two phases of communication, assuming all nodes are correct, assuming the network is correct. Then if all nodes are participating, then we can come up with this simple protocol. So we have all these design choices, and based on these design choices, we can drive from one protocol to another. So if we want to get like this protocol Themis, we can go from PBFT using the first function, which is linearization, get linear PBFT. We can use the leader rotation, get hot stuff, and then we can use the FAIR protocol and get the Themis protocol. So let's talk about the implementation part of the work. In the Bedrock platform, there has like four main components. One is the core unit that defines the entities. By entity, we mean the client and the replicas, the nodes. And it maintains the application logic and the data. Here we can define different workloads, different benchmarks based on what we need in our application. We have a state manager that basically enables the core unit to track the state of all these protocols. So when we implement a protocol, the protocol has some set of states and transitions, and this state manager handles those. And to do that, we define a domain-specific language to basically provide rapid prototyping of BFT protocols. We have the plugin manager. The goal of the plugin manager is that we cannot kind of capture all possible properties that these protocols have. So some protocols have some protocol-specific behavior, or a user wants to add a new dimension, new value to basically this platform. So this plugin manager tries to help us to provide such functionalities. And finally, the runtime unit handles the runtime execution of protocols. It manages benchmarks, it sets up all entities, and enables plugins to run. So here is some simple like DSL code that is part of the PBFT. So in the DSL code, we can define different dimensions, the values that this dimension choose, and the list of roles, phases, states, messages, and all conditions on the quorum and the network that we have. And it reduces the effort of writing a BFT protocol. So if we compare the lines of code for each of these protocols in like Bedrock with the original code, you can see the amount of reduction that it provides. So since we have all these protocols that are implemented, then we can run experiments. I'm just showing one scenario, and the goal of basically showing this experimental result is to say that, okay, what we have implemented in basically in Bedrock is consistent with the basically other results that other people report in other papers. So you can see here, for example, we have the number of replicas that are increasing and the throughput and the latency of different protocols. And this is a failure-free scenario. So Bedrock is an ongoing work, and it was kind of the first step that we have implemented all these protocols. One thing that we are interested to do is to enable user to check the correctness of their protocols. Currently, as a user, you can write a DSL, a domain-specific language in Bedrock, and the Bedrock provides the code, the implementation for you. But there is no guarantee that this code is correct. So one way to do that is to say that, okay, provide some mechanisms to transfer the DSL code that has been written in Bedrock to some other language like TLA Plus or COG and verify that. Another dimension is we know that to ensure the independent failure of replicas, we need to diversify replica implementation. In a sense that if I'm, as an attacker, if I attack the system with some strategy, I shouldn't be able to use the same strategy to attack another nodes. So what we do is we diversify replica implementation. And now that we have this Bedrock, we can write the same DSL code and provide different implementations of this DSL code. We can definitely extend the supported protocols. Currently, it supports partially synchronous protocols, but we can add synchronous or fully asynchronous protocols. The protocol that we have seen earlier on was a fully asynchronous protocol, so probably in the next phase we should able to extend this feature. And then we want to enable scalable transaction processing, so where basically we have different shards, and each shard has like one instance of Bedrock, and now we should be able to provide to support cross-shard transaction where different shards have different protocols, and then we have the cross-shard transaction. And the most interesting part is to incorporate basically machine learning strategies. So you remember the question was to what would be the best protocol for our application? And the answer is basically there is no one size fits all, because we are talking about dynamic environments. The workload is dynamic, the network is dynamic, the pattern of attacks is dynamic. So we cannot choose one protocol for our application. So probably we can use machine learning techniques like reinforcement learning techniques, and then be able to switch from one protocol to another protocol at runtime. That's all. Thank you for your attention. I would be happy to answer any questions.